that in calculus, you have to do a lot of algebra before you can do the calculus. Okay? And so that's sort of what we're doing here. Okay? We're doing the algebra before we can do the calculus. Yes, sir.
I was there yesterday. Do you have another packet of notes?
Yeah, 1.5. Now I handed these. Didn't I hand these out? What's today? Wednesday. Didn't I hand these out on Monday at the end of class? If you're in class at the end of Monday, you have one. If you lost it, you can come down and get another. Sometimes that's where students sell these things on eBay for a little money. You know?
Oh, I didn't know that.
Yeah. Robert Bell's handouts, $5 a piece. All right. So yesterday, right, we simplified a lot of algebraic expressions. Okay. Manipulated some. Where am I? I'm all messed up over here. So we ended yesterday at the middle of page 3 of your handout. The last problem that we did, okay, we rationalized the denominator of this algebraic expression. Well, let's do one more, and then we're going to learn about, get an introduction to the concept of a limit. And we'll be using the results of yesterday's work and this problem in solving some limits. Okay. All right. So we have the complex fraction 1 over x minus 1/3 over x minus 3. Now this is called a complex fraction because we have fraction inside a fraction. Okay? Fractions inside a fraction. So you see this 1 over x is a fraction, 1/3 is a fraction, and then 1 over x minus 1/3 is the numerator, right, in the bigger fraction, and x minus 3 is the denominator. And so the largest fraction bar is the main fraction bar. So you should read this as the numerator 1 over x minus 1/3 divided by x minus 3. Okay. And so we got to simplify this complex fraction. Write it as a single fraction, single quotient with just one fraction bar. Okay. So the first thing we're going to do is simplify this difference of fractions, 1 over x minus 1/3. And you know when you subtract two fractions, you need a common denominator. And so the common denominator for these two fractions is 3 times x. So we multiply the first one, 1 over x, top and bottom by 3. We have 3 over 3x. And then we multiply 1/3 top and bottom by x. And we have x over 3x. And now in the main numerator here, right, we're taking the difference of two quotients with the same denominator, so we can combine the numerators. And we have 3 minus x over 3x all divided by x minus 3. Well, fraction bars are like division symbols, right? So this can be written as 3 minus x over 3x divided by x minus 3. I put x minus 3 in parentheses because if you don't do that, you might just write it as divided by x. And then after that division, you're subtracting 3. Okay? But we're actually dividing by the binomial x minus 3. Okay? Well, so we're dividing through division with fractions. And so whenever you do division with fractions, right, you keep the first number and you switch division to multiplication, and then you flip the second number. So the first number is 3 minus x over 3x. And then we switch division to multiplication. This is how I remember how to do division with fractions, right? Keep, switch, flip. It's just burned into my brain. So I keep the first fraction, I switch division to multiplication, and then I flip the second one. And flip means take the reciprocal. And the reciprocal of x minus 3 is 1 over x minus 3. That's what flip means, take the reciprocal. Well, now we're multiplying two quotients. And you know, when you multiply two quotients, you just multiply straight across. So we have 3 minus x times 1, which is 3 minus x. And then we have 3x times the binomial x minus 3. And again, you got to put the x minus 3 in parentheses because you're multiplying this entire quantity by 3x, right? Not just the x. You might think we're done, but we're not. Because we had this issue yesterday, right? 3 minus x and x minus 3, right? 3 minus x divided by x minus 3 is actually equal to negative 1. Right? Negative 1, just a reminder, eventually we won't have to do this anymore. But negative 1 times x minus 3, when I distribute the minus 1 inside, minus 1 times x is minus x. Minus 1 times minus 3 is plus 3. And then when I switch the order on the right-hand side, I have 3 minus x, right? So negative 1 times x minus 3 is equal to 3 minus x. And when I switch the left and right-hand sides, I have 3 minus x is equal to negative 1 times x minus 3, right? So I can replace 3 minus x with negative 1 times x minus 3. So this is equal to, the numerator is equal to negative 1 times x minus 3. And then I have 3x times x minus 3 in the denominator. And now you can see x minus 3 is a common factor in the numerator and denominator. Cancels. And now I'm left with negative 1 over 3x. And as I pointed out yesterday, the minus sign can be pulled up front of the fraction, front of the quotient. Now, if we, starting with looking at an original rational expression, what can x equal? Can equal 3. Because you have 3 minus 3 is 0. You have 0 in this denominator. What else can it equal? 0, because if x equals 0, you got 1 divided by 0 in this quotient, right? So there are two values that x can equal. X can equal 0, again, that's just to remind you, um, right, preparing you for finding the domain of a function. In WebAssign, when you simplify an expression, you don't have to do this part, right? This is the only part that you supply. It's the answer. All right. So we're going to use what we learned so far in evaluating the limit. It's called the limit of a function, and we're just going to do an introduction. Okay? We're not going to get into detail. Those of you who got to take Calc 1, Math 120, you will get you'll go into a lot more detail. Okay, we're just going to get an overview and learn how to find a limit of certain functions. Okay. All right. So let's look at the piecewise function at the top of page 4. Okay. And so the piecewise function is f of x is equal to x plus 1 if x doesn't equal 2, right? So we use this first rule to evaluate the function f of x as long as x doesn't equal 2. If x is equal to 2, right, the input variable x, the independent variable x is equal to 2, then the value of the function is 4. So this says at x equals 2, the value of the function is 4. Okay. So this is the graph of the piecewise function. Okay. For x not equal to 2, the graph is this line right here. Okay. But at x equals 2, the value of the function is 4. So if the value of the function x equals 2 is 4, right, 2 is the x coordinate, 4 is the y coordinate. So the point 24 is on the graph of the function. Okay. So this point right here is on the graph of the function. Okay. At x equals 2, okay, if this first rule applied for x equals 2, the value of the function would be 2 plus 1, which is 3, and that's where this open circle is. So this open circle is not part of the graph of the function. Okay. This is the point 2, excuse me, 0.23. Okay. So the open circle is not part of the graph of the function. Okay. That point is not in the graph of the function. The black dot is. Well, limits, we use limits to investigate the value of a function near a particular value of x, but not at the particular value of x. Okay? So that's a big difference. Okay? We're interested in the value of the function, in this case, near x equals 2, not at x equals 2. That's what limits help us to do. Okay? Investigate the value of the function for values of x near a particular number, not at that particular number. Okay? So below the graph here, okay, I've taken some values of x and calculated the corresponding values of y, right? The values of the function. Why do they do it during class? Okay. So in this first table, in calculating values of y, right, I use values of x 1.9, 1.99, 1.999, okay? And so when x is equal to 1.9, right, when x is equal to any of these three values, we're using the first rule of the function up here, right, to find the y value. And so when x is equal to 1.9, the value of the function or the y value is 2.9. When x is 1.99, the value of the function is 2.99. When x is equal to 1.999, the value of the function is 2.999. Okay? And so these values of x are just less than the value of 2. Okay? X equals 2 on the x-axis. And you can see that each succeeding value of x is getting a little closer to the number 2. X equals 2. Okay? As we go from left to right. The corresponding values of the function, okay, as x gets closer to 2, the corresponding values of the function are getting closer to the number 3. Okay. 2.9, 2.99, 2.999. Right? Each succeeding value of y, or the value of the function, is getting closer to 3. And so this is what limits help us to do, is they help us to understand what value a function is getting close to as x gets close to a particular number. Okay. So we can represent this trend, okay, this sequence, with mathematical notation. So in mathematics, we use the arrow symbol to represent the word approach. So if I use this symbolism right here, indicates that the variable x is approaching the number 2, or getting close to the number 2 from the left, which means we're using numbers that are less than 2. Because numbers to the left of 2 on the x-axis are less than 2. Okay. So in the table up here, looking at this statement down here, in the left-hand table, the value of the variable x is getting close to 2 from the left, okay? Because we're using values of x that are less than 2. And each succeeding value of x is getting closer to 2. The second row of the table, the values of the function, the y values, right, show that the value of the function is close to the number 3 when x is close to 2. And so we can use this notation to represent we can use this notation that the function x plus 1 is getting closer to the number 3 as x gets closer to the number 2 from the left, using numbers that are less than 2. Similarly, with the right-hand table, I have some values of x that are just slightly greater than 2. So here I have 2.1, 2.01, 2.001, and you can see that going from right to left, each succeeding value of x is a little closer to 2. In the second row, I have the corresponding values of the function for each of those values of x. And you can see in the second row, going from right to left, each succeeding value of the function is getting closer to the number 3. Okay? So, down here, to represent this trend, we use this symbolism to mean that x approaches the number 2 from the right, right? The plus sign in the superscript means we're approaching the number 2 from the right on the x-axis, and that means we're using numbers that are greater than 2. Up above here, the minus sign was in the superscript on the number 2 to mean we're going from the left. Down here, the plus sign's in the superscript on the number 2 to mean we're using numbers greater than 2. We're going from the right. So on the right-hand table up above, right, x is approaching 2 from the right. Each succeeding value of x is smaller than the preceding value and getting closer to 2. And the table of function values, y values, shows that the value of the function is getting closer to the number 3 as the variable x is getting closer to 2 from the right, using values of x greater than 2. Because the value of the function is getting closer to 3 from using values of x from the left, and the value of the function is getting closer to 3 using values of x from the right, we have this notation. Okay? And how this is read, okay, is the limit of the function x plus 1, in this case, as x approaches 2, is equal to the number 3. So this tells us the closer the variable x is to the number 2, the closer the value of the function is to the number 3. Okay? Even though the value of the function at x equals 2 is 4. Okay? So that's what it's telling us. The value of the function, right, it's getting closer to the number 3 as the value of x gets closer to the number 2, even though the actual value of the function at x equals 2 is 4. Okay? So it's talking about the behavior of the function for values of x near 2, not at 2. Okay? So that is a basic introduction to the concept of a limit. Now in calculus, like I said, you'll go into a lot more detail. Okay? So this purpose of this section is to give you an introduction to the idea of a limit, okay, and then use what we've already done in simplifying different expressions to evaluate the limit of a function. Okay. So let's look at the examples at the top of page 5. Now today's quiz is the shortest quiz you've had already. Okay. So I sent you the email. I mean, 10 minutes, probably 9 minutes too much. Okay. So we'll take the quiz around 10:40. Okay. All right. Where am I? So let's evaluate some limits. And this homework has already been released. I don't know if you noticed that, but this homework has already been released. I released it this morning. So in the first case, at top page 5, we have the function x cubed minus x plus 4. Okay. And we want to find the limit of that function as x approaches 2. Okay. So we're asking ourselves, the closer the value of x is to 2, the closer the value of this function is to what number? And so the first step in evaluating any limit is what's called direct substitution. You just put this number in here in for x in the function, and at the and when you do the math, do the arithmetic, if that equals a real number, then that is the value of the limit. Okay. So in this case, we put 2 in for x, the function. We have 2 cubed minus 2 plus 4. And now you gotta follow order of operations. And that is the arithmetic is equal to 10. So this tells me, for this function in parentheses, the closer the value of x is to 2, the closer the value of the function is to the number 10. Okay. In the next example, our function's in parentheses here, and we want to know the limit of this function as x approaches minus 1. So we're asking, the closer x is to minus 1, the closer the value of the function is to what number? Okay. And so again, you do the direct substitution, and you have 2 times minus 1 plus 7, which is equal to 5. So the closer the value of x is to negative 1, the closer the value of this function is to 5, plus 5. All right, those are the easy kind. Okay. What we're going to do next is the more challenging kind. Okay. So in the next example, we have the rational function x squared plus x minus 6 over x squared minus 5x plus 6. Okay. Now, first step, do direct substitution. So I'm going to do it down below here. So when I put in 2 in for x, I have 2 squared plus 2 minus 6 over 2 squared minus 5 times 2 plus 6. And when you do that arithmetic, you get 0 over 0. What's 0 divided by 0 equal to? Can you ever divide by 0? Can you ever divide by 0? No, you can never divide by 0. So this is undefined. However, the limit may still exist. Because remember, the limit tells us what number the value of the function's getting close to as x gets close to a number. So as the closer x is to 2, the closer the value of the function may be to a particular number, right, particular value, even though it's undefined at x equals 2. Okay. So we simplified this rational expression back on page 2 of your notes. Okay. It was the first one we did on page 2 of your notes. Okay. So I intentionally separated simplifying the rational expression from finding the limit. Okay. So this is equal to the limit as x approaches 2. Actually, we'll just rewrite out that first part. Okay. The numerator factors into x plus 3 times x minus 2 over x minus 3 times x minus 2. And because x never equals 2, it just gets close to 2. These two factors never equal 0. So they cancel. And we're left with the limit as x approaches 2 of x plus 3 over x minus 3. And now you can do the direct substitution. Put 2 in for x. We have 2 plus 3 over 2 minus 3, which is equal to negative 5. So this says the closer the value of x is to 2, the closer the value of the function is to negative 5. Even though the function is undefined at x equals 2. So we're only interested in values of x near 2, not at 2. All right, and the next one, we have x squared minus 4 over x squared or x cubed plus 8. Okay. And we simplified that one on page 2 as well. Okay. That was the second problem on page 2. Okay. And so when you do the direct substitution, we have minus 2 squared minus 4 over minus 2 cubed plus 8. And again, you end up with 0 divided by 0. And so the function is undefined at x equals minus 2. But the limit may still exist. So we have the limit as x approaches minus 2. And when we factor the numerator and denominator, we did that on page 2. We ended up with x minus 2 times x plus 2 over x plus 2 times x squared minus 2x plus 4. Well, because x gets close to minus 2 but doesn't equal minus 2, the factors x plus 2 cancel. And now we can do the direct substitution. So we put minus 2 in for x. And then you do the arithmetic. And when I did the arithmetic, I got minus 1/3 after reducing the fraction. So that says the closer x is to minus 2, the closer the value of the function is to minus 1/3, even though the function is undefined at x equals minus 2. Okay? So remember, limits tell us what the value of the function is near a particular value of x, not at a particular value of x. Okay. Any questions on that? Okay. So let's take our quiz.